Yeah, let recording us to start. Just a minute. Yeah. Okay. Hello all. Welcome to the fifth session of the Alumni G Meet. So I'm indeed very happy to have a person from the very first batch which I got to teach at Shastra after joining Shastra. So from the 2013 batch, Abhinav. I'm not going to give a complete biopic of Abhinav, which I already shared, but I just want to say a few sentences on his passion for thermodynamics. All I can say is it has never changed, right from what I have seen probably from September 2011 when I saw him at the Thermodynamics 2 class until now. And I don't think also he will talk anything other than thermodynamics for the rest of his life. So that's a passion for thermodynamics, and that's a passion with which he connects everything around with just thermodynamics. I should rather also tell probably this to the current juniors. I used to, as usual, play my tricks. And once even I asked, what if he does not get a PhD topic or a master's not connected to thermodynamics? And he was very instantly in his response, he said, until he gets a thermodynamics topics or a thermodynamic oriented topic, he will wait. Okay, he will not just like that do any master's in thermodynamics. So that's the passion of the speaker today. So I'm very happy to have Abhinav joining this series. Thank you, Abhinav, and you can continue. You can share your screen also.
Sure, yeah. Thank you, sir. Thank you, sir, for that introduction. Let me quickly share my screen. So, I think my screen should be visible now.
Yeah, it is starting.
Okay. Okay. Can everybody see the screen?
Yeah, I'm able to see.
Yeah. Okay. Yeah, sure. Thanks.
Yep.
Okay. So, like what Naren sir basically introduced, like today's topic is basically on this. The topic title, the title of the talk is basically a pun on this current situation where we are all like social distancing and in lockdown. So there is this usual joke that I mean, in thermodynamics, an isolated system is kind of redundant because it's of hardly any use typically. But in the time of a pandemic, we are pretty much just confined to our house. So we can consider each of ourselves to be basically manifestations of isolated systems. So that was kind of the motivation for the title of the talk. But then, what I want to do with this talk is it's going to be fairly short on the technical side. I just want to give some examples of the applications of thermodynamics in solving some real-life complex problems that I've worked on through my master's and my PhD. And then also like a couple of slides on like what to look for in a PhD and like how to navigate a PhD. And then I basically want the rest of the half to kind of be more of like a conversation on like questions that people might have on how to apply to a PhD, what to look for in a PhD, and like what is the life of like a person doing a PhD. Okay, so with that, so this is kind of the basic motivation. So you can think of problems in real life being split into this time and length scale, where you have stuff that goes down to angstrom on the left. So that's like 10 power minus 10 basically, and then going all the way up to like a millimeter or centimeter scale. And then you have a similar time scale. So things that are really small, like things that are in the angstrom scale, like basically like motion of electrons, all your quantum particles, they typically happen in a femtosecond or a picosecond time scale. And then you have your normal atom, say like a hydrogen atom, things like that, which typically happen on a nanosecond time scale. And then you have much bigger systems, things like polymers, things like say like proteins and biomolecules and things like that, which are kind of this intermediate scale between what would be atomistic and what would be proper continuum. Like proper continuum would be your typical bulk thermodynamics, essentially. What we typically learn in undergrad thermo, like phase equilibrium and these kind of bulk processes. So things that fall in between are what is called as MESO-SCALE. So the goal of this talk is to kind of give one application in each of these. I've been fortunate to work on every single time and length scale so far. So I can kind of present one single problem that I worked on and how thermodynamics is applied there. And so these are like the pertinent equations, are kind of the key equations that play a big role in these length scales. So if you go all the way down to quantum, this is the Schrodinger equation for an n-electron system. Much of my PhD deals with solving the Schrodinger equation for solid oxides, but then we still want to connect to macroscopic properties. So although you would solve the Schrodinger equation to get the ground state energy of a system, ultimately you would still connect that somehow to realistic conditions. So you would still have to calculate your free energy and entropy and stuff. Things at the atomistic and mesoscale, it's typically motions of atoms. So this is basically a form of Newton's law, which just says that the forces between atoms can be calculated as the negative gradient of the potential energy. And in continuum, and I think everybody here should be familiar with this, this is basically phase equilibrium. I've just chosen one single example here. This is fugacity of a solid phase being in equilibrium with this liquid phase. So it's kind of a solubility problem. So with that, that'll probably be a good prelude to the first topic, which is jumping directly into continuum classical thermodynamics. And so this was something that I worked on when I started out my master's with ECU. So the basic kind of idea of this project was, so there are these compounds called polycyclic aromatic hydrocarbons. So things that are, so you can think of compounds like naphthalene, chrysene. So they're basically multiple aromatic rings. So it's like two benzenes combined and things like that. These are typically environmental pollutants. And there is usually, so to get rid of them, since they're extremely organic, you'll probably have to use an organic solvent as well. But then organic solvents themselves are pretty toxic. So there was this whole bunch of experimental studies that was done that you could use this thing called subcritical water. So subcritical water is basically pressurized water at high temperature. So it's water above its boiling point, and it's highly pressurized. And there was some basic evidence at that point that when you basically raise the temperature of water under pressure, it's not as polar anymore. So it can basically dissolve some amount of organic compounds. So, but then what we wanted to do is basically to see if we can use a thermodynamic approach to get like a predictive model on like what temperature and what pressure you need for this solubility to actually work. So phase equilibrium then becomes the basic and the hardcore principle in this. So these equations should be fairly familiar to everybody. It's very similar to vapor-liquid equilibrium, but this is a solid phase in equilibrium with the liquid phase. Of course, the solid phase is already pure, so that is just a standard state already. But then the liquid phase can be written as the activity coefficient of the solute times the solubility of the solute in terms of mole fraction times ideal liquid fugacity. And so that ultimately gives you this expression for the solubility. I'm not going to go into the derivation, obviously, where this activity coefficient is simply now the ratio of the fugacity coefficient in the actual liquid state to the ideal liquid state. So then the problem essentially becomes, can we get a suitable model for finding these activity coefficients? And I think in Thermo 1, Thermo 2, I think all of us would have used UNIFAC, and people have actually used that, but then they found that it usually doesn't work simply because there is also a pressure component involved. So you would typically need a pressure volume relation. So which means you would need to use some kind of an equation of state to actually model this. And so what we used here was actually the Peng-Robinson equation of state. Everybody should be familiar with that. It's a very simple cubic equation of state, but then if you do it for a mixture, so in this case, it's basically the hydrocarbon mixing with the water, you would need these mixing parameters. And the mixing parameters are usually very ill-defined. And in our coursework, we would typically take some kind of approximation. But those typically don't work. So what we basically did was to apply these modified mixing rules. And one such mixing rule is kind of shown here. It's called the linear combination of the Vidal and Michelson mixing rules. So that's the equation for that. And it basically still involves calculating this excess Gibbs free energy. And the mixing rule, in fact, uses one version of the unifact to calculate that quantity. So this is all basically applying things that we've learned with respect to phase equilibria and actually solving a problem. And then we actually tested it out. So this is showing a parity plot so this is the log of the mole fraction solubility calculated using experiment versus what we predicted. And you can see that it's a really, really good fit. I mean, those in data science and things like that would probably appreciate this plot. So the basic goal of this slide is that you can achieve a lot of things. You can solve really complicated problems. You can get good predictive accuracy even by using classical thermodynamics, as long as you know what to apply and how to apply it. Okay, so with that, I'll go down. So this is now one scale lower. So this will be the MESO-SCALE. And so we were interested in this problem of basically self-assembly. There is this molecule which is, so I used to be in New Jersey before this, and New Jersey is a big pharma hub. And there were a few pharma industries who were kind of interested in trying to understand the self-assembly of this block copolymer. So these are basically two block copolymers that are like biocompatible. So people were interested in applications for targeted drug delivery and things like that. This is methoxy polyethylene glycol block polycaprolactone. This is the actual monomeric unit of the block copolymer. So now, if you were to simulate this by doing conventional molecular dynamics, you will never be able to hit these kind of like time scales. So this is about 2000 nanoseconds. So it's about 2 microseconds. That's way beyond the time scale that current computers can do molecular dynamics on. So the idea was to basically coarse-grain the system. So we basically take this block and represent it, as like a separate bead. And then you can say that these blocks that we form interact with each other using some kind of potential. I think in our thermo course, we would have learned the Leonard-Jones potential. And so we basically say that this actual atomistic representation can be represented by this weird block structure, and that these blocks basically interact with themselves using a pair potential, like a Leonard-Jones potential. Now, much of this goes into what would be introductory stat mech. We are all pretty much used to thinking about classical thermodynamics, where you kind of have absolute equations. But then in terms of statistical mechanics, you'll have to start to think in terms of probability distributions. So if I were to simulate this block polymer, essentially, I would basically get a distribution of, say, the bond length. I would get a distribution for the angle. And so they're usually kind of almost Gaussian with one particular peak. So basically the notion in StatMech is that this value over here, so for instance, this NaC1 NA angle peaks at somewhere between 150 to 160. That is going to be the expected value or the macro state. And these are all the different manifestations of what would be the expected value. And so what we did was to actually do the all atom simulation, and then you could get the distribution from that, and then do the actual coarse grain simulation, and you can match the distribution. That way, you know how these two bonds stretch, you know how this angle behaves, and so on. So that's how you kind of parameterize this model. So it's basically parameterizing your interaction between the polymers. And then we actually wanted to test if it would self-assemble, because we are taking, we're taking an actual chemical system and then making it into a very abstract space. And so what we did was we basically randomly distributed a whole bunch of these molecules and then just let them run, and you see these really spherical clusters that form. And this is basically a manifestation again of the free energy winning. Obviously, this is entropically a more preferential state because polymers just want to be randomly distributed. But then the key thing to note is that polyethylene glycol, those who are fond of chemistry would have realized that this is highly polar. So it likes water, but polycaprolactone has these giant hydrocarbon chains, which makes it pretty non-polar, close to apolar actually. And so it doesn't like water. So then what typically happens is they self-assemble to these core shell structures where the polycaprolactone is on the inside. So those are the red beads, and then the green is the polyethylene glycol tail, which is pointing towards water. So it basically maximizes its interactions, thereby minimizing its net free energy. So that's a basic self-assembly problem. There are a lot of people who work on this scale, working with biomolecules, and there is a lot of thermodynamics involved in actually understanding all of these phenomena. So I will just quickly give one more example for this MESO-SCALE. So the idea is that if you were to use these as drug carriers, they would have to interact with the lipid bilayer because much of our epithelial cell lining is are essentially covered by lipid bilayers. And so this is a model lipid bilayer. We used DOPC, which is dioleo phosphatidylcholine. And we wanted to see the interaction of these micelles with the lipid bilayer. And this is another manifestation of minimizing free energy. So this was the actual micelle. So we checked two different micelle combinations. So this is obviously very highly hydrophilic because the polyethylene glycol is 17 units and the PCl is only 3. This is largely hydrophobic because the PEG is only 5 and the PCl is 9. So this is a PEG 5 PCl 9 unit. You can see that it still has that core shell structure with the PEG pointing outside. But then once it starts interacting with the bilayer, so the head group of the bilayer is highly polar and the interior of the bilayer is basically hydrocarbon. So it's extremely apolar. You can see that when it interacts, it basically changes to a Janus formation, where this extremely apolar hydrocarbon polycaprolactone wants to be internalized. And then the polyethylene glycol is very happy to interact with water and the polar head groups. So this is another instance of things basically orienting themselves so that they get the minimum free energy. And then you can do what is called enhanced sampling methods. I will not go into that because that's a whole new area. What we used in this is basically what is called umbrella sampling. So you can essentially get what is called the potential of mean force, which is basically the free energy. So this is the free energy of interaction of this micelle with the bilayer relative to the distance from the center of mass of the bilayer. So what this is basically telling you is that if it's extremely hydrophilic, it wants to get out. So the zero is down there. It's about 400 kilojoules per mole. It just wants to be chucked out. It wants to be in water. But then if you make it more hydrophobic, it doesn't want to be in water anymore. It actually wants to go somewhere into the bilayer. So now, so for somebody formulating these kind of nanopolymeric micelles, this kind of gives them like a preliminary idea on like what ratio to use for the block copolymer so that you can actually facilitate suitable interaction with the bilayer. So now we'll go to the atomic scale. So this was a problem that a few people were interested in trying to understand this supercritical oxygen because it is very important in combustion chambers, in jet engines and rockets and generally propulsion systems. So there were actually a lot of people who write CFD codes who wanted to know exactly what was happening and if we could get a more accurate characterization of the thermophysical properties of this phase so that they can actually feed it into CFD models when they're modeling flow and turbulence and things like that in like a combustion chamber. And so that was the basic motivation for this. So there had been some prior experimental observations in other supercritical gases of this liquid to vapor like phase transitions that happen in the supercritical phase. So now everybody should be familiar with this. So now this is basically showing a density as a function of temperature at different isobars, so different pressures. So if it were a first order phase transition, say for instance, liquid water becoming gas, what would happen is this would go down, and then there'll be a sharp drop at the same temperature before going out. So that would be the phase change. And then if you were to look at it in terms of, say, the enthalpy, that difference would basically be the latent heat. We see something similar in the supercritical phase. It's not a first order singular phase transition, but more of a dynamic phase transition, in the sense that there is no discontinuity. So you do see a continuous variation in the density when it's more dense, more liquid-like, and then if you go to higher temperatures, it becomes more vapor-like. And this shows the heat capacity now as a function of temperature. So if it were a first-order phase transition, the heat capacity should go to infinity because, as I just told you, you're going to have latent heat because of like a non-uniform jump in your enthalpy at a fixed temperature. But then we don't see something like that. It doesn't quite go to infinity, but what typically happens is it peaks. So it kind of maximizes. So basically the enthalpy also goes through something like this. So more of a continuous phase transition. And then we observed that even transport properties, for instance, the diffusion coefficient of just oxygen atoms diffusing amongst themselves has almost like an Arrhenius type behavior with temperature. So it has some kind of activation barrier as you go to higher temperature and then transition to lower temperatures. And structurally also they're affected. So this goes into percolation theory, so I won't talk much about that. But typically what we observed was that at lower temperatures, they typically form percolating clusters, and then once you go to higher temperatures, they become more diffuse. And so you can then define what is called this Wiedemann line for oxygen. So the critical point is down there, and then what we are saying is that there is this line which basically corresponds to all of these phase transitions that happen, but they're dynamic phase transitions. So it's more liquid-like down there, and then more vapor-like down there. So so this has very realistic applications to people who are modeling these on like a larger length scale and time scale, where they will probably have to use say a different equation of state, different parameter operating regime versus if they're operating. So there are very practical applications to this. And then finally, so this is some work that I did that got published last year. This is part of my PhD now. So for my PhD, I mainly work on with an angle on basically designing materials and generally like electrocatalysts for these sustainable energy applications. So one such example, and this is a combined experimental and theoretical work, so you can see the direct application of thermodynamics here. Basically, we had two of our experimental collaborators who are really experts in solid oxide fuel cells. So if you look at a solid oxide fuel cell, what typically happens is you have an anode where there is usually a hydrocarbon that gets oxidized, and then you have cathode where oxygen is reduced, and then O2 minus ions are transported across a solid state electrolyte, goes to the other side, and that completes the cell. And then through the reaction, you basically get energy out of the reaction. So you can use it for like current and stuff. The main problem with solid oxide fuel cells is kind of what happens at the cathode. So basically the reaction at the cathode. So the oxygen reduction is usually pretty slow. It has pretty poor kinetics. So people try different ways on actually improving the catalytic activity of the cathode. And so one such thing that was tried was there's this material called lanthanum strontium iron oxide. What our experimental collaborators found was that if they basically did like a sub-monolayer coverage of a lanthanum oxide on top of their actual perovskite structure, they found that they had very good activity. And then if they did a multi-layer like deposition of the lanthanum oxide, that activity died. And then if they added a basically an iron oxide layer on top of the usual perovskite, it didn't show any enhancement in activity. Only this showed an enhancement in activity. And so these are what are called as electrochemical impedance spectra. I think Niranjan will probably relate to this. So you can see that, so basically when they do really small amounts of deposition, so this is basically a Nyquist plot. So this is like the polarization resistance. So really small amounts of lanthanum oxide deposition reduces the resistance, and then you keep adding more and more lanthanum and the resistance increase. And then they basically also did this thermal cycling where they found that when they add this lanthanum, maintain it at a particular temperature, resistance holds. And then if they go to a high enough temperature, they get back their pristine surface. And so they didn't really understand what was happening. So they wanted us to actually model this. And so what we did was to basically, again, it's just another phase equilibrium problem. So you can think of when a crystalline material forms a particular surface. So say it wants to form this surface versus this surface. What is the driving force for that? So the thermodynamic driving force is that any surface is always in equilibrium with the bulk. So you're always going to cleave the bulk and form a particular surface. And so any orientation of the surface, any different termination can be modeled as a phase equilibrium problem where the surface and bulk are in equilibrium. And so this is again Gibbs phase rule. Everybody in who's taking thermo or who has taken thermo should relate to this. Now, in this case, we basically consider lanthanum iron oxide, so it's LFO. So it has three components, and there are two phases in equilibrium. So C minus P plus 2. You can specify three variables now. So it's 3 minus 2 plus 2. And obviously, we need the operating temperature to relate to the experimental conditions. Oxygen partial pressure is needed because that's another operating condition. So if oxygen partial pressure is used, that also fixes your oxygen chemical potential. So then you can only specify the chemical potential of one of iron or lanthanum. So in this case, we use iron and then express lanthanum in terms of iron. And so if you do that, you get these two limits. So these would basically be the precipitation limits. So if iron's chemical potential were to go larger than that, then iron oxide would precipitate. And if it would go less than that, lanthanum oxide would precipitate. So you want to be in, so you can use this region to kind of compare the stability of the different surfaces. So this is the surface Gibbs free energy as a function of that chemical potential. And obviously, the one that has the lowest free energy is going to be the most stable. So what we find is that this surface here, the pristine surface they had, is actually the most stable. But then if they were to do any kind of, these kind of, like these depositions, which has these defected structures, they basically are down there. So they are extremely unstable thermodynamically, but they could be kinetically trapped. So which is why they see that there is some enhancement at mid temperatures, but then once you raise the temperature to 973, so close to 1000 K, it goes back to being pristine. So this kind of rationalizes why they were seeing those trends, and it also aids in better design of cathodes for solid oxide fuel cells in this instance. So with that, that's kind of the end of the technical talk. So these are all the folks that I need to thank. This is my PhD advisor, Alex, and this is E. I've had a lot of fun working and learning from both of them. These are two funding sources. These are all the software and computing sources without which all of the previous results that I showed would not have been possible. And I also want to emphasize that all of these software, so GROMACS, Plume, ASE, Quantum Espresso, are all open source. So if anybody is interested in picking these up, I mean, like especially things like GROMACS can be run on a regular desktop computer. So you can always, and there are online courses and tutorials to pick up molecular dynamics and things. So these are all feasible at simple lab scale. And so yeah, so with that, I just have a couple of slides, and then maybe we can make it more of a conversation. And so what I thought of was, this is basically titled Navigating the PhD. So why do people want to do a PhD, and why should you do a PhD is, the first thing is you need to find something you are passionate about, because this will occupy your life for probably for the rest of your life. But then if you're as part of your degree through your master's and your PhD, that's a good chunk of at least 7 or 8 years. And you need to be absolutely focused that you will like what you're working on for that period of time. Because if you lose interest, then it becomes very difficult for you and the person advising you. I have seen a lot of people who want to jumpstart their career by doing a PhD. I would strictly advise against that, because PhD is not going to give you better pay or career benefits. You will have to take it up only because you are truly passionate about something. Because at a time when people have full-time jobs, you would still be a grad student. You would be earning far less than somebody who has a full-time job. So it's not going to increase your financial benefits or anything like that. So don't get into that for, don't do a PhD for, if that's your motivation, don't do it. This is often an important question that usually comes up to me. Should I care about the ranking of the institution, be it in India or abroad or wherever? The repute of the institution actually does not matter as much for a PhD. Just make sure that the advisor is good and the lab you work in is really good, because you will spend a lot of time with them, and you need to gel in with the lab, and they should also like you. There is also this pressure of publishing a lot of papers, and then if you publish more papers, then you somehow accomplish much. But I would generally say quality of publications is always greater than quantity of publications. So if you're looking for a PhD lab or a PhD advisor, look at their Google Scholar page or look at their lab website and see, are they publishing too many papers in really low impact journals, or things that are not really relevant, or are they publishing only a few papers but in good journals? So that is usually a good barometer for picking out where you want to do your PhD. And then there is usually this notion of doing a PhD in theory versus doing experiments. I would say that PhD in doing computational theory is not any different to experimental research. You still go through the same thing. You have a hypothesis of a particular problem. Instead of going to the lab and actually conducting experiments, you simulate or model it on a computer, and then you prove or disprove the hypothesis. So it's essentially the same thing. Several of the software that most people use now are all open source, and there are several general purpose programming languages that everybody can learn. And this is usually another question that I get, which is, should I have a coding background if I want to go into theory or computation? I would say no. A majority of my lab mates actually came from experimental backgrounds. They were just fascinated by the research, and they basically picked up coding in Python and things like that in 6 months or so. It's not so. It's just another skill that you will learn in your PhD. And the final thing is, this is a key point now that we are all in this pandemic. So even when the entire world comes to a halt, if you're doing theory, you can still get stuff done, because you just need a computer and a strong internet connection, so you can truly function as a regulated system. Yeah. So with that, I will stop, and I'll also thank Naren sir for this opportunity, and for all of you tuning.
Yeah. So any questions? I think this is the only presentation which started with length scale and time scales. Yeah.
Yes, sir. Yeah, that was the background. Yeah.
Yeah. Yeah. So any particular questions anybody wants to ask? So I hope all second years and third years, probably including final years, will be slightly confused that what you are talking. So all I want them to enjoy is chemical engineering is much more than what they have seen as part of their curriculum. And you can literally do very fundamental things which is needed actually in applications later on, that is required for designing applications as such, as he said, for electrode design, or be it for phase equilibrium. So you need somebody to actually work with very fundamental systems. I think for many batches I have told that his master's advisor at Rutgers, Professor Chu, is actually from the lineage of Prausnitz. whose data you are actually using. Okay, so that's one thing and information. Yeah. So any hello, I think there's a crosstalk. Shwetava, I think it's supposed. I think okay. So any particular questions regarding, like, should you pursue PhD? Is it worthwhile pursuing PhD? Right?
Hello, sir.
Or what to focus? Yeah, you can ask. Who is that?
Yeah, I'm speaker, sir.
Yeah, Shrikar. Yeah, ask.
Hello, Anna. I just had a doubt in the first, beginning of the slides, which involves, classical thermodynamics can be used to predict or do whatever you want. You just have to know what to do and how to do. Can you throw some light on what are the what's and how to do? It's very general statement, what and how. I mean, at least in the classical sense, not to go into the MESO-SCALE.
That's a good question, Shrikar. So I mean, there are clear limitations to classical thermodynamics. For instance, you cannot solve for instance, the self-assembly problem, or like the supercritical phase that I was showing you. You probably cannot solve that using classical thermodynamics, mainly because of these are phenomenon that are that have these many body effects and things like that. But then classical thermodynamics can be used for solving, so my point with that slide was that in our undergrad thermo we learn VLE, vapor liquid equilibria, but then there are different manifestations of phase equilibria. So if you know, say for instance, like a particular equation of state or a particular classical thermodynamic approach would work for solving a particular problem, then go ahead and apply it. That's my so before you jump into doing some really complicated like a molecular dynamic simulation or things like that, which are obviously computationally way more expensive, if that problem can be simplified in terms of a classical thermodynamics model, then that should be your criteria. You should first target it. You should first try to approach it with that angle, and then go into more sophistication.
Thank you.
Does that answer your question?
Yes, sir. Yes, sure.
Yeah, I mean, if there are like more questions on generally about pursuing PhD and generally like graduate school and like research and things like that, please feel free to.
Hi, Nat.
Hi.
So this is nothing related to thermodynamics or anything. Just wanted to, out of curiosity, I'm asking. So, how did you find that? Okay, fine. This is some interesting field, and I want to pursue it further. How did your interest in thermodynamics grow? And my second question is, do you but from seeing the PPT that you gave, I'm telling it frankly, because I couldn't follow it much. So I'm sorry for that. I couldn't follow it much. But apart from this interest, do you spend time on something else as well, or does this occupy the whole time of yours? Because a lot of equations are involved, and so you have to break your head with it, right? So I just want to know out of curiosity.
Yeah, good question again, Hari. So the first question was how did I get interested in thermodynamics? I think part of that credit goes to the teachers that I had. So Naren sir probably takes a big chunk of that credit, because Thermo 2 was a very, very interesting course. I think all of us in our batch will agree that it was. I mean, we truly learned something properly in that. We actually understood, and for once, like it was. We actually understood the concepts like really well, because it was taught really well, and so that kind of sparked the interest. And I would also say that I think Naren sir works on this FOSI project with it's like a Scilab textbook companion project, and so I got to code YVC Rao for that. So basically went through every single solved example in YVC Rao, so that that kind of sparked probably a very firm interest. That I mean, I actually got to read through the book like page by page essentially. And then again, I would also say that my masters I got to work with ECHU, who, as Naren sir said, is pretty famous. Is really famous in thermodynamics in StatMech, and I took graduate thermodynamics with him, and yeah, he's a phenomenal teacher as well. So I think you getting an interest in something has to do with the professors who taught you one particular course. That's typically why people like that particular course. And then with respect to your second question, yes, if you're doing a PhD, be it experimental or theory, it's going to occupy pretty much your entire life for the duration of the PhD. You will still have time to do other things, but yeah, you will be working in lab at least 6 or 7 hours a day, bare minimum, and then mostly you will also be working on the weekends. So it does take up your entire life.
Yeah. Thank you, Anna, and all the best for your PhD.
Oh, thanks.
So any other question? Yeah, but I have a follow-up question.
Yeah.
It's finding passion is okay, but a great, I mean, the issue which we have with many people now, or at least the present generation, is how to keep up that passion, because we have lots of distraction. In your time, there is no WhatsApp, but here now we have a lot of things. How to keep up the passion and not get distracted? Finding a passion, yes, I agree, it's a difficult task. But even after you have found the passion, how to stay firm on that passion and not look for immediate results or gains?
Yes, sir. That's yeah. I don't have a good answer to that, and that is kind of what I was indicating with one of those points in the slides where I was saying that when you're looking for a lab, when you're doing a PhD, don't look at the quantity of publications, because so that I feel is usually the way your passion can get sustained. Is if you end up in a lab that is, that truly cares about the science that they're doing, then you will not see like 5 publications in a month, because they really want. Yeah, so that environment, I think, is what will sustain you.
Yeah, but that's at the PhD level. But I'm talking about the undergraduate level. So in the undergraduate level, between 3rd and 4th year, I have lots of colorful distractions. I have colorful attractions, and people wants to experiment lot of stuffs. So how to keep up the passion at the adolescent age of 3rd and 4th year undergraduate?
Okay, so 3rd and 4th year, what I can say is, at least from my experience, there are some really good research, like fellowship programs, like the summer research fellowship. I think Indian Academy of Science does one, and all the IITs do one. So I spent one summer through the Indian Academy of Science and one summer through IIT Madras, where you actually work in a lab. They also pay you per month for the 2 months in the summer. You actually get to work in a lab, and you work on a project, so you get like hands-on experience. So in your summer, if you're thinking of like an internship opportunity towards research side and not industry, then something like that would be an opportunity where you then you're still part of that lab environment. So then you are fascinated by what other people are doing in the lab, and so your interest is kind of sustained.
Okay. So to maybe an information to all others, I still remember his final semester BTech project was hardly, I think, 20 or 30 pages on radioactive pollutant dispersion in upper atmosphere. Okay, so and it was very different at that time to convince the panel or the group of faculty that he didn't do an industrial project, he didn't do a conventional whatever it is, and of the 20 or 25 pages what he had as a BTech project, probably the panel or some XYZ of the review felt that nothing was comprehensible. So, and I was fortunate that I was called to see that and say that whether this person has really worked. So now I can tell that Abhinav, like I said that, okay, sir, this person has understood and he has literally applied. So it's we should appreciate. So that's what's that. And to Abhinav, I actually told the other thing, probably in our discussions, that I told that you have taken a topic which is probably not very attractive. If you lose grades, is that okay? That's what I asked. I hope Abhinav will remember that. And he immediately said, yeah, I don't mind. I said he was one of the toppers of his class, and that time we never had 9 grade. We just had grade point 8 and 10. So if the 10 goes, he has to land on 8, grade point 8. And I said that will affect your GPA. And he said, I don't mind. Okay. So that is his passion at the final semester. It's a very small, probably 30 pages. The cardboard was weighing more than the pages that was there inside, and it was a radioactive pollutant. So we were telling, okay, so tomorrow, if something happens in IG car, how much time it will take for a radioactive nuclei to reach? This is something like was his focus on the 8th semester. Okay, so that's something.
So who was the project guide, sir?
So I spent each semester, since I took the that accelerated program, I didn't have any coursework, so I spent that semester at Baba Atomic Research Center.
Okay.
So I did that project over there along with people over there. So they were all basically physicists. So it was a very interesting problem to work on. It's a lot of modeling work.
Yeah, so there's one question from Purvaja on the chat for you, Abhinav.
I'll just open one second, yeah. Okay, how do you narrow down the schools either for master's or PhD with respect to the course or topic that you're interested in? Yeah, great question. I think that is probably the most important thing that will decide where you want to go. And I would advise that you spend a considerable amount of time, looking at that. So what I did was, as Naren sir already pointed out, I was very interested in, people who, my choice of applying to schools was, the first thing was to look at their department page and look at their faculty list and see if there was somebody working on any topic related to thermodynamics. And then, so that was like my first criteria, to see if there was an active computational or theory-based thermodynamics work that was happening in the department. So based on that, I basically had like about 15 or 18 schools. And then from that, I kind of filtered out. So the way you do that is, obviously, you can't apply to all of these top ranked schools, because chances are you're going to get rejected more often than not. So what you then do is you take like 3 or 4 safe schools that you know that you have a good chance of getting into based on your profile, and you apply for like 2 or 3 really ambitious schools that you might have a shot at getting into. So you then end up with like 8 or 9 schools. So my basic criteria was, I didn't really care about the ranking of the schools. I only cared about the research that was happening, and if there was somebody doing research in an area that was of interest to me. So you should use that. I would suggest that you use that criteria. That will obviously give you a range of schools with like very different ranking or reputation, however you want to call it, and then you can mix and match based on like the different schools that you end up with that list. But the key criteria should be that if you're going to do a master's or a PhD, always find out, because I mean, there is no point in just doing coursework again as part of masters, because most of the concepts you've already learned in your undergrad. So the purpose of masters is to, or a PhD is to actually do some valuable research and pick up those skills. So just make sure that there is somebody who's working in an area that is of interest to you.
Okay.
I think there was one more. Yeah. How to get cheered on research cause, you won't get the results you need every time. And about PhD, it's entirely like trial and error. So how do you face this? Okay. So okay, the first part of the question is yes, you don't get results immediately. That is why people end up doing their PhD for like 5 years at least, 4 or 5 years. So I would say that so the best motivator is yourself, right? So if you're really passionate and interested about that subject, you will continue to work on it. You will continue to work on it no matter what, because it will break your head that you are not able to find a solution to that problem. So now, if you're really that passionate about it, you will work and you will get results. Now, the other angle is obviously your lab environment and your and the role that your advisor plays. So that's why I put a point in my slide saying that make sure that you work in a lab and you have an advisor whose lab environment is usually good and the advisor is really good. Basically, if you're stuck in something, you immediately go to your advisor and they should be able to help you. And most advisors do that. So it is not that you're always on your own. You are encouraged to solve the problem on your own. But if you do get stuck, there are senior people in your lab, postdocs even, or your advisor itself, who will come and kind of direct you in a different way. And I think so. The second part of that question was PhD is entirely like trial and error. Again, I think I kind of covered that with my first answer. It's not entirely trial and error. Yes, you will largely be independent. You are expected to be independent, at least after your first year, once you've picked up the basic skills. But there are always people to help you out. So make sure you end up in a lab where people help you out. That's the most important thing. And I think even Naren sir can share his experience, like with his lab and advisor. I think.
Okay. Yeah. Anything else? I would just add, like for me, who's this?
So Abhinav, I have a question. This is Vaishali from 2015 batch.
Yeah.
Hi. Actually, thank you for the talk today. I'm not sure what is your interest. What are your plans after PhD? But if you become an academician, that would be really great, and it would benefit the student community. So my question is, for someone who's inclined toward.
Yeah, before Vaishali asks, just two small things. Yeah, if he becomes a teacher, at least probably Shastra can have a guest lecture from a good thermodynamic teacher. That's point one. And point two, and not only a good thermodynamic teacher, he is very generous. Probably he is very generous than the present teacher. So that is also one good nice thing for a student. The second is this is the first lecture where we have started the speaker based on Near Virpam. Okay, so Vaishali, you should be happy. You asked.
Yes, I'm really thankful.
Your super senior accepted.
Yes, definitely, sir, definitely.
Yeah, go ahead.
Yeah. So my question is, for a student who has completed their UG, PhD or PhD, what they look for in the job is, are they able to use their brains? Is there any, for example, I am working in a manufacturing unit where I would say for the past 2 years, I have not applied any concepts of thermodynamics. So, and even in the interview panel of many companies, you feel even the panel members are more interested in questions with respect to heat transfer, mass transfer, or fluid dynamics, fluid mechanics, and mostly thermodynamics is something ignored. So if a person enters industry and he is not into academics, so what are the fields he should look for if he is a person who is inclined towards thermodynamics? So what kind of job he should look for if his inclination is towards thermodynamics? Yes.
Okay, got it. Okay.
Yeah, Abhinav, just before you answer, I wish to Vaishali, thank you for bringing this question. I will recollect or remind Abhinav before he
Yes.
graduated, I mean, probably in the final year, when I was speaking with Abhinav, we had a kind of a challenge. I told him that you should come and convince that if there is no precision thermodynamics, how much loss is there in terms of design or in terms of product for an industry.
Yes,
Otherwise,
I would. Yeah.
so I hope, Abhinav, you will remember that. So I asked you that you should come back and convince that if great thermodynamics was not done, then what is the loss in industry? Unless you convince out explicitly, it is very difficult for somebody to absorb the significance. Yeah.
Got it. Yeah. So, Vaishali, great question, and Naren sir, yeah, good follow. Great summary of that as well. So, I would say currently, based on current existing, chemical process industry, things are already optimized, so they don't need anything new in terms of thermodynamics. But then, if you look at job opportunities where somebody who is interested in doing this kind of fundamental modeling, it will basically be more in like the renewable energy side. So those are still technology that is up and coming. So you will still need to actually optimize many of your systems. For instance, there are a lot of companies that make commercial fuel cells now. So they might be interested in understanding these kind of phenomena. And then there is actually a pretty big company that was just being acquired by a company in Norway that they basically produce hydrogen from water. So it's basically an electrolyzer company. And I think Niranjan can also comment on this at some point. Is electrochemistry is a really big field, and I know that Niranjan works very actively. And battery technology and energy storage and these kind of things do require a lot of people who understand thermodynamics. So I know a lot of theory has gone into understanding lithium ion diffusion and finding superconductors for lithium ion and things like that. Really fundamental work. So if there is any opportunity, I would say currently for somebody who is doing really fundamental work, I will not say that it would be in traditional chemical process industry like oil and gas or things like that. But actually, there is probably opportunities in pharma as well, if that is considered a traditional field. But if you consider a hardcore manufacturing like oil and gas or like fine metals and things like that, things are already optimized, and companies don't want to change anything. I can actually there might actually be opportunities for people who also do automotive exhaust and things like that. People becoming more and more environmentally conscious. So designing of systems for that, there are some very fundamental applications there. So I would say if you want to do more fundamental stuff, you should go into an area that invests in R&D currently, and basically industries that like core industries that invest in R&D currently would be these renewable energy technology companies.
Yeah. Thank you.
Yeah. So
Yes. Yes.
yeah, I'll just add to what Abhinav said. Two of Abhinav's own classmates who are there now in Europe on the other side of Atlantic, Nitish and Subhash, they are also into this kinds of modeling, but on a very, very small scales. I think one is doing on MD, and I'm not sure what is the other person's. But they are also on to development of novel catalysts, which will give very high selectivity. So that's a part of the shell. Both of them are part of the shell. And Niranjan, are you there? Niranjan?
Yeah, I'm here. I'm listening.
Yeah. Niranjan can actually throw light on, because Niranjan is, just before Niranjan speaks, I just want to give an intro. Niranjan is anyhow going to speak after a week. But he is into the field of batteries, fuel cells, and he has got a spectacular experience in one of the finest labs company, which you will come to know in his talk. But I just want Niranjan's comment on how far is thermodynamics important in development of newer materials that he is looking after. Yeah, Niranjan. Yeah, Niranjan.
Actually, thank you so much, Abhinav, for this Great talk. Actually, I mean, I'm not really good with thermodynamics right from my undergrad, but it's great that you developed that interest right from the undergrad days, and here you go, you're doing your PhD, and I think we spoke last week that you're looking into postdoc positions as well. I wish you good luck. I'm pretty sure that you're really going to do well in whatever you do. I just wanted to, yeah, like in terms of when it comes to industries, I feel that thermodynamics has a great application. People actually save a lot of money before directly trying something out. If you do some modeling and simulation, especially when you apply thermodynamic principles, I think industries save a lot of money. So your starting point even before you start something. And Naren sir's question, for batteries, I think there are so many new materials, especially from the cathode material side. So you wanted to see how the interaction is between different atoms. And I think Abhinav mentioned in one of his projects, that like interaction between the particles is very important, because that's how you can charge your battery effectively. So most of the contribution comes from the material. So it was interesting because I never thought from this perspective of how thermodynamics is applicable, because I've seen a lot of computational modeling, but those were from the structural chemistry. It was never related to thermodynamics. But today after this, I learned that there is another interesting perspective. It greatly helps how fast you can charge your battery, how well you can improve its lifetime, something like that.
Thank you, Niranjan. So any other questions? We are already 9:15. So if there are any other questions, or otherwise we can, it's good time to close. So before I close, probably I will wish to take some one or two closing remarks. So anybody from 2013 batch, so it's okay. So I will first begin with Abhinav's batch only. I think I saw Rukmini, you are there? Yeah, Rukmini. Rukmini? I think she is not able to hear. Can you talk, Rukmini? Pace Mudima. Okay, yeah, okay, no issues. So I think she is held up. So Rukmini's talk we will have sometime later. Okay, so where you will actually know the value of time management. So that's something that we have to learn from Rukmini. So probably I will ask Neeraj itself. Neeraj?
Yeah, yes, sir.
Yeah, you yourself can give a closing remark for your classmate friend.
Okay, so I mean, one thing with Abhinav is I've always like looked up to him in terms of the kind of passion that he showed. I mean, through and through, there was one person who knew what he wanted in life, like right from the start. I think, I mean, he was the one person who I felt was like, he always had, okay, I mean, I took chemical engineering because I wanted to, and I'll do this. Like through the years, I think he developed interest in thermodynamics, and then he took it up, and then he's still doing it. So that kind of passion, I think you saw in his work as well, though it was Greek and Latin to be most of it, except for a few terms thrown here and there, which I study. I mean, which I remember Naren sir mentioning. But yeah, I mean, overall, though I might not be able to entirely appreciate the technical content of the presentation, I would say that he's someone who's strived through this thing to like pursue what he wanted. So I think you can take his word on pursuing PhD, like narrowing down on topics, etc. And he's like very, very helpful when it comes to even be it academics or I mean, he'll even go out his way to help you guys out if you need any advice. So, yeah.
Yeah, thank you, Neeraj. So, anybody from the current students who want to talk? I mean, you can just talk and then we can close the session. Any current student who is willing to volunteer? No, there is no current student. So, any current student who is willing to talk? Ah, yeah, of course. Why not? Anybody, whoever wants to talk, just unmute. Yeah, Akash, you can speak. What happened? Yeah, Akash, you can speak.
Hello, sir. Can I?
Yeah, Akash.
Hello. Sorry, sir. It's not audible here, unfortunately.
Yeah, Akash. Okay. Who is that one who said, can I? I don't know. Who's...
It's Rukmini.
Ah, Rukmini, yeah. Come.
Yeah, it's nice to hear from Abhinav after a long time, actually. As Neeraj said, he has been consistent with his performance throughout all the 4 years, to my knowledge. And I actually... Yes, sir.
Rukmini, sorry to interview. You should tell, right? Appavum Abhinav pesradhu namalku puriyala, ippavum puriyalendriya.
Illa sir, abdila illa. I'm able to understand, but I'm just telling about his consistency.
Yeah, okay. Yeah, carry on.
Yeah, and I really pitched in because of the topic that was very interesting, actually. When we saw during the pandemic, how do we isolate ourselves just like the systems? So I wish I was very happy to hear the session. I joined in the middle, but I was able to understand here and there with the thermodynamic knowledge that I know. And all the very best for his coming years.
Yeah, thank you, Rukmini.
Thanks. Rukmini.
Yeah, I think Akash could not speak, I suppose. He's a second year student. Anybody else wants to give a closing comment, or shall we close?
Yeah, sir, I forgot to wish him, so I'll just wish him, Sabi, all the very best for your, I think you're about to complete your PhD, is it? Or
1 more year, hopefully.
Yeah, okay. So that and for the postdoc.
Thanks, Neeraj.
Kill it. That's all.
Yeah, Akash, you can speak. If you are able to connect, you can speak.
Hello. Hello.
Yeah, Akash, carry on.
Anna, first of all, wow, now literally, what about your thermodynamics knowledge and your interest over that? I just saw your LinkedIn page where Naren sir suggested you for a grade of thermodynamics. Wow, I'm so impressed now. Like, I thought mechanical engineers and others were too intense about thermodynamics, and chemical engineers were not that much core about that. And it entirely you changed that opinion, no? Like that your impression on thermodynamics is like, I just want to have some passion like that and want to approach some research works, and it's enthusiastic now, your speech. Thanks for that. No,
Thanks, Akash. Good luck with everything. I mean, so the main point of this was to convince people that you can do some really fundamental theory that has applications to real life as well. So.
Okay, so we will end the session. Thank you all. Thank you, Abhinav. So for the first technical session on a Google Meet. So I hope we will have many more sessions from many people else. So tomorrow we are going to have Hariharan, who is also there on this call today from Australia. So he's from the 2018 batch. So let's meet tomorrow. Thank you all. Bye.
Bye, sir.
Bye.